All right, I think it said it's recording. Okay, I'm going to zoom in a little bit. Okay, so just one last thing. So we talked about QR eigenvalue, the QR algorithm for finding eigenvalues in really excruciating detail on Friday. So one just quick thing I added that I thought might be kind of fun is I made a little demo showing how the regular Gram-Schmidt algorithm compares to the modified Gram-Schmidt. So all that this demo does is it creates a bunch of random vectors. And then every pass of this continuous Gram-Schmidt algorithm where I sort of pick a direction and orthogonalize, it basically sees how that set of vectors spanning the column space changes. So it's the process of finding the Q matrix in QR factorization. And the vectors, here I have a 10 by 10 matrix, but I can only view vectors in 2D on my computer. So this is going to be the columns of some matrix that I'm trying to orthogonalize. In the traditional Gram-Schmidt algorithm, as I run it, the vectors don't always change. And the reason for that is I have to actually get to one of the vectors before I subtract it through from all the others. So traditional Gram-Schmidt has this idea that if, I have the 0th column, the 20th, the 40th, the 60th, or the 80th column, so I have some columns in my matrix, I don't actually touch those columns until my iteration gets to them. And so Gram-Schmidt traditionally has this really sort of jumpy structure where most of the column vectors aren't touched until the loop gets to them. And this is in contrast to the modified Gram-Schmidt, where every single step of modified Gram-Schmidt, I modify all of my other vectors. So here, they continuously change because all of my column vectors are getting modified each loop of modified Gram-Schmidt. And you'll recall that the reason that this gives us an advantage is because you immediately start orthogonalizing all of your column vectors at once rather than waiting till you get to one with your index. And so this gives you some nice advantages when it comes to condition number and overall stability of the procedure. And just to see what that looks like a little bit more sort of systematically, here what I've done is I've gone and I've done traditional Gram-Schmidt and modified Gram-Schmidt, and at every step of that iterative algorithm, I've computed the condition number of the matrix that I'm finding the orthonormal basis of. And you can see what happens, which is that originally I start out with the exact same matrix. The condition number is just what it is. But with traditional Gram-Schmidt, I'm one by one modifying the columns. And so my condition number only improves very, very gradually. But with the modified Gram-Schmidt, I modify all of the columns. I immediately subtract out that first vector. And so I get this almost exponential drop in condition number. And both of them will give me the same Q matrix. So I should get the same solution. So they end in the same place. They start in the same place. But the modified Gram-Schmidt gets me there way faster because it gets rid of all of this redundancy in the column super fast. So it's just something nice that you can get when you look at the modified Gram-Schmidt. Okay. So I wanted to give maybe an example of when you might use large-scale matrix inversion methods. So you recall that I have this network of collaborators among astrophysicists. So this is this data set that shows all potential collaborations among astrophysicists in a 10-year period starting in the 90s. And it has this structure where there's a lot of people who are collaborating with each other. And there are a few sort of isolated nodes. These are people who had fewer collaborators than people in the bulk here. So I can actually use Gram-Schmidt to analyze the structure of that graph. And I write a bit about it here, but the basic idea is I'm going to take the adjacency matrix and I'm just going to find its eigenspectrum. So if the collaborator network is an n by n matrix, I have n nodes. Every element of that matrix is a connection between nodes. So it's an n by n matrix. If I normalize that matrix and I then just find the eigenspectrum, the leading eigenvectors basically give me scalar values assigned to each node. The eigenvectors of an n by n matrix are n by 1 vectors. And those actually tell me what the long time limit of a random walk on that matrix looks like. I won't get into the theory because it's not really relevant to the algorithm side, but I write a little bit about why that's the case. But the important thing is that when we introduced this collaborator network and we talked about random graphs, we talked a lot about how you can have random walks on graphs where I talk about hopping from one node to another at some rate that depends on who I'm collaborating with. Rather than doing all that trouble, it turns out that just the eigenspectrum of your adjacency matrix gives you that information. And that's because you can think of the adjacency matrix as defining something like an operator that propagates random walks on that network. And this idea that you could just take the adjacency matrix of some graph you're given, you find the eigenvectors, and then you stare at them and try to interpret what they tell you about your system. This is the whole idea behind spectral graph theory, which basically involves taking your graph, which is an adjacency matrix, and doing various types of eigendecomposition to try to understand properties of that matrix. So here we're just looking at the eigenvectors of the adjacency matrix. And the important thing is that it turns out that the first eigenvector more or less tells me what the long-time average distribution of random walkers on the matrix looks like. Okay, so that's one application of when you might want to apply some of the QR algorithm to a really big matrix, because recall this is a 4,000 by 4,000 matrix. It's a really big matrix. And so being able to use iterative algorithms instead of trying to do the schoolyard eigenvalue calculation can come in handy for this. And this is implicitly what a lot of solvers use behind the scenes when analyzing large matrices. And one argues that the structure that it gives you maybe tells you something about who's highly collaborative, who's a little bit less collaborative, as well as the secondary eigenvectors maybe identify communities within this group of physicists that maybe have secondary dynamics. Okay, so that's a little bit of random graph theory. And if you're interested in graphs, I'd encourage you just to read a little bit over this notebook where I talk a little bit about the different kinds of random graph algorithms that are out there. Okay. So we're gonna go ahead and change gears and talk about, so far we've talked about finding eigenvalues and eigenvectors of square matrices. That's because those are matrices for which this problem is well defined. But a lot of the time, especially when we're working with data, we really are dealing with matrices that are intrinsically non-square. So we have m not equal to n. And so this is where we're going to get into the problem of using a singular value decomposition, which generalizes the idea of eigenvalues and eigenvectors to non-square matrices. Okay, so recall, I talked about this a bit last time, that you can always think of a Hermitian matrix as defining something like a transformation of a set of points. So if I have some Hermitian matrix, that's a matrix that is symmetric or whose elements are conjugate transposes of each other, but if it's real valued, it's just symmetric. And that always has this interpretation that it takes a set of points and it just squishes it and rotates it by some amount. And the argument that we had is that those rotation directions and the amount that I'm squished along them tells me something about my eigenvalues and eigenvectors. And the reason that that's the case is because you can always interpret a Hermitian matrix in terms of defining a potential function. And the reason for that is that if I have some potential, right, which is a scalar that takes a vector as an argument, the first gradient of that gives me the Jacobian matrix, right? So if this is a potential that takes an n by 1 vector and gives me a scalar, if I take the gradient of that, I should get an n by n. And so then I get an n by n matrix J, which can be written as a matrix of partial derivatives of my scalar potential. So Hermitian matrices are special because they always, if I have a matrix that's Hermitian, I can always define an equivalent scalar potential associated with that matrix. So this isn't always the case, right? Because I could always pick some weird matrix that's not symmetric or is not its own conjugate transpose. So in that case, it might be possible to define something like this, but this might not necessarily be well defined. But Hermitian matrices are special because they always have this interpretation as defining some potential. Even if you aren't given the potential, it exists if you have a symmetry in your matrix. And the famous example that this pops up in modern computer science is most of the time in machine learning, you're optimizing a scalar loss function. So this is something like the error of your fitting procedure. That's usually a single number, like how accurate you are. And so a lot of the times taking the scalar of that loss function with respect to something like the model parameters, or taking the gradient of that loss function with respect to model parameters, that will implicitly give you a Hermitian matrix because of the fact that you have a scalar loss function. So Hermitian matrices are actually super important even for everyday sort of machine learning stuff. But they have this nice thing that they always define a physical process. You can always think of them as one and the same. Okay.
So machine learning, the X and the Y, those are like the parameters.
Yeah, or it could even be something like Y could be the predictions of a model, and X could be the actual points that the model that we observe, and so we're trying to maybe compute the difference between predictions and what we observe or something. That would be the interpretation I'd use here, is maybe X is what you saw and Y is what your model says you should have seen, and so we're trying to get this as close to possible by modifying the model. Okay, so just to give an idea, and I drew a diagram of this in the last lecture, but I wanted to maybe just do it in code. So what I'm going to do is I'm just going to write a Python function that's going to generate a bunch of random points in a uniform disk. So this just takes n, which is a number of points, and it just gives a radius. So it samples these points, and then we're going to define a random Hermitian matrix. And I'm just going to do that by sampling a random 2x2 matrix adding it to its own transpose, and then this operation symmetrizes the matrix. So it's just a really simple way to make a random Hermitian matrix. We're just going to see what that does to my set of points. Okay, let's run that. Okay, so this is what they look like before I apply that matrix. So each point is just 2 coordinates, so it's a 2 vector. So I apply the matrix once, and it sort of rotates and stretches, which is what Hermitian matrices always do. And then if I apply the same transformation again, you can see it doesn't rotate much more, but it stretches a little bit more. And in fact, if I were to repeat that operation a whole bunch of times, I eventually would get that this cloud, it gets narrower and narrower until it eventually stretches out along one direction. And this direction actually corresponds to the eigenvector associated with the largest eigenvalue of that Hermitian matrix. So in other words, if I repeatedly apply a Hermitian matrix to some set of points, eventually the set of points just gets squished out along the principal eigendirection. So the leading eigenvector of a Hermitian matrix is super important because it basically tells you the asymptotic behavior of applying that matrix a bunch of times. And so in the homework, we give an example of the power method, which is a method for finding eigenvectors. And that basically exploits this idea because it says that if I don't know my eigenvectors, I just am given my matrix, I can just pick a random direction, apply my matrix a whole bunch of times, and that'll give me the direction of the leading eigenvector. So the power method basically uses this dynamical systems interpretation to numerically find the leading eigenvector of some matrix, which is super useful. And again, this is exploiting the fact that all the Hermitian matrices do is they rotate and stretch. And so once I've aligned with my principal eigenvector, I just keep stretching until eventually I have a really narrow set of points that's just distributed along the largest eigenvector of that matrix. Okay. And here I tried to take that code I did above and write it as like a little widget. So we'll see if this works. So here I've used NumPy to calculate the 2 eigenvectors of my matrix, and then I'm just going to start with this uniform point cloud. And then this is just repeated applications of A to the point cloud, and you can see it very nicely squishes and gives me the principal direction. Okay, and the power method, which you'll see in the homework, only finds the leading eigenvector, but you can guess how you might generalize that to find the other eigenvectors, because you can see that, for example, the second eigenvector for a 2x2 matrix is always orthogonal to the first. So you might imagine a principled way of constructing that. In more dimensions, you need to compare, for example, shrinkage along different dimensions and stuff like that. But the basic intuition that you tend to sort of stretch along one direction is going to be the key to a lot of these Krylov subspace methods, which the book talks about in some detail. Okay. And then all I've done here is I've just, to sort of emphasize this, I basically just calculated how much this point cloud extends along this direction versus that direction. And you can basically see that as I repeatedly iterate the matrix, the span of the point cloud along each direction more or less matches what I would expect from calculating the eigenspectrum. And it turns out that the span along the direction is always proportional to the eigenvalue associated with the principal eigenvector. So basically, Hermitian matrices, each iteration of this method compresses or stretches by an amount that's equal to that associated eigenvalue. So the amount that I decreased from here to here tells me that that eigenvalue is probably around 0.5 because it basically halved along that direction. Likewise, there's some stretching here that is proportional to whatever that eigenvalue is. So the eigenvalues basically tell you the amount you stretch, and the eigenvectors just tell you how much you stretch. Okay, so Hermitian matrices are super nice. Symmetric matrices have these nice properties. They're easy to interpret. And the reason that we like them is because Hermitian matrices are very useful for understanding some of the properties of non-square matrices. Okay. So the idea here, and I write a little bit about it here, but the idea here is that if I have some non-square matrix that has shape n by m, I can actually use that matrix to define 2 new matrices. One of those matrices could be the left product of A with itself. So if I take that matrix, I multiply A by its own transpose on the left, that'll give me an m by m matrix. So I'm contracting along the n dimension. Conversely, if I do that in the opposite order, so I take the right multiplication with the transpose, that'll give me an n by n matrix. So for every non-square matrix, I can come up with 2 possible square matrices that just have the 2 possible shapes, depending on the order in which I multiply by their transpose. The reason that that's useful is it suggests that this matrix, this AT times A or A transpose times A, this probably has some eigenspectrum associated with it. And then this matrix also has some eigenspectrum associated with it. And so singular value decomposition is a way to write my original non-square matrix in terms of the eigenspectrum of this matrix and the eigenspectrum of this matrix. And we're going to sort of glue together those vectors, some of which are going to be n by 1, some of which are going to be m by 1, in order to recapitulate my original n by m matrix. That's kind of the idea behind singular value decomposition. Okay, so if I define my two matrices as this and this, singular value decomposition is going to, let me just see if I write it down here. Okay, singular value decomposition is basically going to say that I'm going to have one matrix U. This is going to be my m by m matrix. So this is going to be ATA, and this is going to be AAT. Yeah, I think I got that order right. So one of these is going to be m by m, one of these is going to be n by n, and then this jagged matrix here, the sigma matrix, is going to be the one that stores the actual eigenvalues associated with the transform. So the actual derivation of SVD, it's in the book. It's not super elegant, but the basic idea is that you should think of it as SVD as trying to find the eigenspectrum of this, the eigenspectrum of that, and then stitch those two things together to write your original matrix back down. Okay. So I'll go ahead and maybe skip this because I think that that's confusing. Okay. Okay, so in principle, if I wanted to do this transformation, let's say that I have some eigenvalue solver I'm happy with, I would take my ATA matrix, and I would just orthogonalize it using Gram-Schmidt or whatever my favorite method is. That would give me a set of eigenvectors of this matrix. I'd write those as column vectors. I'd call that U. Then I do the exact same thing for AAT, which has a different shape of n by n. Then that gives me a new matrix of column vectors V. And it turns out that I can write my original matrix as that m by m matrix times an m by n matrix times an n by n matrix. And these things, when I multiply them all out, will give me an n by m matrix back. Okay. Yeah, and there's various interpretations of singular values. Chris Rycroft's notes have one interpretation that I kind of like. It talks about using the stretching intuition. The book uses kind of a different convention to talk about these, but you can kind of think of it as if I have eigenvectors of some point cloud that I define as this matrix AA. You can think of sort of applying the A operator as mapping that to a new space where I'm going to point along the U eigenvectors. That's kind of what singular value decomposition corresponds to. Okay. So if I write out SVD sort of in terms of what the shapes of the various things are. So if my A has, let's say I have n rows here and m columns, so I'm going to use the convention that n is the number of rows here. One way that I could write that out is that I have my square matrix. So this is me taking the product such that I get an n by n. So that gives me that. I could also take a product such that I get an m by m. So that gives me this matrix. I'm going to need to orthonormalize them in order to get a basis associated with each matrix. And then the sigma matrix is going to be the one that sort of converts those shapes into each other. And that matrix ends up having this nice expression where it has a diagonal structure up to the smaller of the two numbers. So here I'm using the convention that m is smaller than n. So we'll have m diagonal elements, and then everything else is zeros. And then I'll also have a bunch of zeros here below where this diagonal runs out. And so I have two square matrices that are orthonormal basis sets associated with these two products. And then I just have this rectangular matrix that just has this diagonal set of values. Okay, so the nice thing about doing that is that if you want, you can actually truncate your U matrix because of the fact that if I'm doing a multiplication with a bunch of zeros here, then all of these elements are just going to implicitly get multiplied by a bunch of zeros. They're not going to get used. And so as a result, you could imagine cutting off all of these elements from my U matrix. Those are the unused basis vectors. And so I can basically get sort of a truncated U matrix that just is the basis vectors that are spanned by the column space of A. So full SVD is what Python and I believe MATLAB compute by default. And so this will give you two square matrices, U and V, as well as this sort of jagged epsilon matrix, which has the singular values. But some packages, like I think maybe the Julia solver does this. They give you actually the truncated matrices. So if you ask for SVD of a matrix, it'll give you a square singular values matrix. It'll give you the right V matrix, but then U will not be the right shape. And all it's done is it's just cut off these eigendirections that aren't spanned by the columns here. Okay, so U and V are just the orthonormal bases that are associated with ATA or AAT. That's all that U correspond to. Okay. So the reason I'm really big on this sort of dynamical systems view of matrix multiplication because I think it gives some insight into a lot of these iterative methods for calculating various properties of dynamical systems. So in the case where you have a non-square matrix, it gets a little bit fuzzy, right? Because if I have an n by n matrix, if I have some initial condition that's an n by 1 vector, I apply the n by n matrix, I get another point in the same space. But if I have a non-square matrix, I'm implicitly going to do something like a projection or something where I'm going to pull my vector to some new space where it has fewer components. So the interpretation of this, there's actually a way you can think about this in terms of a type of system called a skew product system. So there exist types of systems out there where I have variables whose values update based both off of their own values and based off of external values. So this is an example of a skew product system. So the thing to notice here is that xt updates on x, y, and z, yt updates on x, y, and z, but z only updates on itself. And so in other words, if I want to track the dynamics of z, I just need to know what z most recently did. But if I want to track the dynamics of x and y, I need to know their previous values as well as z. And this is a type of object called a skew product. And it has a very sort of storied history in dynamical systems because it corresponds to systems with causal structure. By which I mean, I could say that z causes x and y to do stuff, but x and y never affect z. So I could say that z is causally disconnected from x and y. The reason I like that is because then if I wanted to track x and y's dynamics over time, I could actually write that as a non-square operation on the previous values of x, y, and z. So I can interpret non-square matrices as sort of me requiring information about external variables to update my dynamical state, which gives me some idea as to why, for example, I have so many zeros that I end up truncating, because it turns out that some information doesn't propagate through. Like x and y need to know about z, but z doesn't need to know about x and y. So I end up with a bunch of zeros in the expansion when I write this out as a series of equations. So, SVD is one of these things where everyone has their own favorite pocket interpretation. The book really likes talking about it as sort of like a compression problem. I like Chris's notes because he talks about it sort of as the stretching of different directions. But I like to use it as sort of thinking about how this would generalize this idea of matrices operating on initial conditions. Okay. Yeah, and I give a little demo here, but I don't think that that's super exciting, so we'll leave that aside for now. Okay. So the reason that SVD is useful, the reason it's useful to be able to take any matrix you want and write it out as one orthonormal basis times a rectangular matrix times a new orthonormal basis transposed, is that this actually allows you to take systems and approximate them as sums over rank 1 representations of your system. So if I write down, let me copy this down just so we can see it. So if I take the definition of SVD, and I'm just going to put it there so we can see it. So this is the definition of an SVD of a matrix. You can use some quick matrix math to show that this is equivalent to writing A as the sum over outer products of the eigenvectors of U, the eigenvectors of V, with a scalar that corresponds to the diagonal element of the singular value matrix. And this is actually a pretty powerful idea, because it basically just is saying that this matrix multiplication is equivalent to that, and that's because of the fact that this sigma matrix is diagonal for the first m entries. And so what that means is that if A is a full rank, or is a full rank n by m matrix, or has a rank m by n matrix, I could write that as an outer product between the first eigenvector of U, the first eigenvector of V, weighted by sigma. Then I could find the second eigenvector of U, the second eigenvector of V, weighted by sigma 2. And I can basically write this as a sum over low rank matrices. And this is nice because this gives this idea that maybe I could truncate this matrix series. So for example, if I have m singular values, so U is an m by 1 matrix, V is an n by 1 matrix, and these outer products give me m by n matrices. You could imagine instead of using this whole sum, I could just take a couple of the singular values that I might want to. And this is useful because it allows you to take square matrices and compress them using just a couple of terms in this sum over outer products. So the way this is going to work is I'm going to use an example that I think is very Texan. So this is a square matrix, right? This is an image of Hank Hill. I don't know, maybe this is like too old for the class. And this is implicit. This image is implicitly a matrix where every value is between 0 and 1. So it's just a grayscale image. And this matrix is a rectangular matrix, right? It looks like a matrix, and it turns out that it has 372 rows and 248 columns. So it's not a square matrix. So in principle, the eigenspectrum of this matrix is not well defined. Okay, so I can perform the singular value decomposition on this square matrix. You can do this using Gram-Schmidt on the image times itself, et cetera, et cetera. I'm going to just use a built-in to do this. So a lot of built-in SVD solvers will just give you the U matrix, the sigma matrix, and V as matrices. Okay, so I run that, and when I run that on this image, which has this shape 372 by 248, it's going to give me three things. So it's going to give me my U matrix, which is, again, a square matrix. So that should be an orthonormal basis set. It's going to give me my V matrix, which is a different orthonormal basis set. And then by convention, this version of SVD just gives me the diagonal elements. So it's going to give me the 248 diagonal things. And if I wanted to, I could do something like sigma equals S times NP dot I. And this would give me that full matrix for the compressed SVD. So this would be equivalent, but just to save a little bit of space, it's just going to give me the diagonal elements. Okay, and recall that if SVD is valid, then I should be able to write something like my image is equal to U at sigma at V dot T, and this will give me back my original image. Okay, so this just splits my matrix into these parts. So all I'm going to do is I have this series of sigmas, and I'm just going to plot what the different singular values are of Hank Hill as a function of their index. Okay, and I'm going to do this on a logarithmic scale. Okay, so these are the diagonal elements of this sigma matrix that correspond just to these values here. Or likewise, they correspond to these coefficients in the summation over the outer products here. Okay, so if I do that, I see something that's pretty common for most types of data you might encounter, which is that the magnitude of the singular values drops off pretty fast. So I have one like super big singular value, and then maybe I have a couple of significant ones, but pretty quickly, maybe I hit a plateau, but pretty quickly they start to level out. So that tells me is that when I go and I compute my sum over outer products, if I have these sigmas that weight each outer product of the eigenvectors, the terms in the sum decrease pretty rapidly in their amplitude because the sigma basically sets the scale of the sum. So this gives a hint that maybe this summation is going to be a truncatable thing. Okay, and again, the reason that this works is because if A is m by n, no matter how many terms I include, the product of an m by 1 times an n by 1 vector is always an m by n matrix. So every term in the sum has the right shape. It's just how many terms I choose to retain in that sum. Okay. So, you know, the singular values of Hank Hill drop off pretty quickly, which suggests that maybe I don't have to retain all the terms in that sum to reconstruct my original matrix. Okay, so what I'm going to do is I look at this and I think that, you know, I have a long plateau here, so maybe I'll just take the first 20 singular values. And I'm going to see how well I can do reconstructing my full matrix of Hank Hill just by truncating this set of singular values. Okay, so up here I found these matrices. So this was my big matrix, this was my singular values, and this was my my other smaller matrix. So I'm just going to truncate this by keeping only the first 20 elements. So I'm just going to truncate at the first 20 singular values. So after I do that, I'm going to end up with rectangular matrices, where U is going to be long by short. S is going to be my 20 by 20 sigma matrix, and V is going to have my 20 truncated values by my short element M. And if you multiply these three, you can see why this happens, which is that if U has an outer size of 372, all the 20s get contracted over, and then I should get 372 by 248 back. So everything contracts out where I truncated. So if I want to approximate my image using these truncated things, I just have to multiply all these things together. And when I do that, I can actually get a kind of low fidelity reconstruction of my image. So it captured most of the structure. We can recognize it as Hank Hill plus some grayscale terms. And that's because of the fact that most of the information was stored in the first few singular values. And this is nice because this is kind of the whole idea, not just behind image compression, but just generally behind dimensionality reduction in a lot of different contexts where it pops up, which is that in principle, you know, I have this high dimensional matrix. I have two matrices, the 372 by 372, and the other is 248 by 248. But information about the overall shape isn't evenly stored across the column space. Some directions in that space matter more than others. And so singular value decomposition basically asserts a sort of a hierarchy among your eigenvectors and says that some of them matter a lot more than others. And that importance ends up being proportional to the size of the singular value associated with it. Okay, so one quick thing that you might notice is that conveniently enough, all of my singular values are positive real numbers. And this is just a consequence of the spectral theorem, right? So we talked about how we're working with Hermitian matrices, right? A dot AT times A is a Hermitian matrix, as is A times AT. So Hermitian matrices always have real positive eigenvalues. And so as a result, I always have this nice thing where I can interpret these in terms of just sort of a decay towards zero. Okay, so that's compression using singular value decomposition. So now all I'm going to do is I'm going to try to do a video where we see how the accuracy of my reconstruction changes as I vary the number of singular values. So we'll see if this runs in a reasonable amount of time on my computer. Okay, hopefully that worked. Okay, so this is what happens if you try to use just one term in the outer product. So the sort of stripy matrix is what you would expect if I just took some column vector and multiplied it by some row vector. So I have a single vector times a single vector, and the outer product is going to have this super redundant structure because there's no way to have differences across these elements if it's just one vector outer producted with another vector, so you get this crisscross pattern. But interestingly enough, because of the singular value structure, because these are eigenvectors, you can already see that it kind of is capturing some of the structure in the image just with this rank 1's approximation of Hank Hill. So now I'm just going to, as I run the video, we're just going to add more singular values back in. And this corresponds to just adding more terms to that sum over the outer products of the U and the V eigenvectors. And you can see that pretty quickly, we recover most of the original structure of the image. And so I would basically say that, you know, this image is highly compressible, which means that the first few eigenvectors of its left or its right square matrices capture most of the information you need to see the image. And in the case of this, because this is a cartoon, we can actually kind of back out why it's the case that we had this really, really abrupt drop-off in singular values. And that's because if I look at this image, you know, there's a couple of scales here that are basically set by where there are lines, right? So there's like this average scale corresponding to like the gap between things, but there's not a lot of really high frequency information, right? He doesn't have any skin texture. That would be a really high frequency component. There's also not a background or anything really elaborate. So the number of sort of discrete scales that we need to capture in this problem is super small because it's just a cartoon image. And so as a result, it ends up being super compressible. So the converse of this would be if I had some really crazy image, like in my group, we sometimes work with images of turbulence. So turbulence is famously an example of something that has detail at every single scale you can imagine. So for that, it's not like a cartoon because there's so many different things you have to account for to approximate it. And so if you had an image that was maybe more realistic or had a bunch of different scales, you generally would expect to see a lot slower drop off here. You want to have this nice thing where you drop a couple of orders of magnitude right off the bat. So in other words, the singular value spectrum has this loose interpretation in terms of sort of the number of distinct scales or sort of the complexity of the different things that are available in your image. And you could imagine, maybe I'll add a demo of if you take like an image of an actual person, you'll find that generally this has a lot slower decay because there's a lot more information that you have to compress into your vectors. Okay, so that's singular value decomposition. And then one thing that came up last year, and I think that there are some people here who probably know more about this than I do, is that this idea that I can take some matrix and I can write it as a sum over outer product states, right? So I have my matrix. This is one n by n matrix, that's another, and they're weighted by this sigma term. This is not unlike density matrices that sometimes pop up in QM. Where the idea is if I have some set of basis elements, like some set of pure states, sometimes I can approximate the density matrix as a sum over outer products of pure states, which are each just eigenvectors weighted by the probability of being in that state. And you can imagine I could come up with some scheme where I would truncate my density matrix with just the most probable states. I'd have to renormalize so it would be a true density matrix. But in principle, this is basically the same thing. The one difference is that generally this is going to be just a square matrix, so you don't really have to worry about, the left and right thing. But this idea of expanding some matrix in terms of a series of outer products, this is more or less the same idea. So, low rank approximations of high rank matrices pops up in a lot of different contexts. Okay, so that's singular value decomposition. And I just like to think of it fundamentally as defining this because I think this is a really satisfying way of thinking about arbitrary matrices. Are there any questions on that before I talk about pseudo-inverses? Okay, so then one thing that having knowledge of the SVD is going to allow us to do is going to allow us to deal with cases where we need to invert a matrix, but the matrix itself is non-invertible. So this is called a Moore-Penrose pseudo-inverse. And this is arguably the only thing you need to know about linear regression is this one thing, because this is basically what underlies all linear solvers is this idea that you can define a pseudo-inverse. Okay, so this is a lot of linear algebra, but it's actually relatively simple what it is. So let's imagine that I have some linear problem. So just AX equals B, same linear problem we've always been solving. But now we have a case where A is a non-square matrix, which means that B and X are different shaped vectors, right? So matrices change the shape of vectors when they're non-square. So I'm going to say that X lives in Rm, B lives in Rn. So A sort of glues those two spaces together and converts me from one to the other. Okay, so if I'm given A, I'm given B, and I want to solve for X, now I can't just do my sort of lazy LU factorization that I was doing before, because I know that I can't invert a non-square matrix. However, it turns out I can actually get pretty close if I'm willing to relax my requirements that I perfectly solve this problem, and I instead say that I just want to get as close as I can to solving this modulo some error. So we'll define that a little bit more precisely downstream, but the idea is that if I have a lot more rows than columns, I might not be able to perfectly solve this, but I might be able to do pretty well by approximating an inverse. Okay, so the idea behind the Moore-Penrose pseudo-inverse is that I'm just going to take A and I'm just going to replace it with its singular value decomposition. So I quite literally just plug and chug there. And just like you always do with these, you're going to one by one move the elements of your matrix over. So because U is a Hermitian matrix, I can just move it over normally. And then I'm going to make a really specific assumption, which is that in order to invert my sigma matrix, which you recall is my actual troublesome matrix, that's the one that has a non-square shape, I'm going to define a new matrix that corresponds to my original singular value matrix with every singular value inverted along the diagonal. So the exact same way we defined the inverse of a diagonal matrix, but now we're doing it on a non-square matrix. But we're going to call that inverted matrix the pseudo-inverse of this matrix. And we're going to plug it into our substitution there. So all I've done is first I move U over, then I move this over using the pseudo-inverse, and then finally I'm going to just move V over. And I'm going to call this series of terms where all I did was I transposed the two SVD matrices that I already had. And then I did this special thing with my sigma matrix where I inverted every diagonal element. I'm going to call that combined matrix the pseudo-inverse of the matrix. And the argument is going to be that if if A was a matrix that maps me from M space to N space, this series of operations, because it reverts it does the U's and V's in opposite order. This maps me from N space back to M space. Okay, so the reason that this is going to work is that in the case where I can't actually fully solve for X, this particular matrix is going to basically be the matrix that gets me as close as possible to the X that minimizes the difference between the left and the right-hand side. So the pseudo-inverse can't guarantee you an exact solution to this problem, but can guarantee you the closest that's possible in the sense of minimizing the average error between the components. And this kind of gets down into the lore of overdetermined systems. If I have a bunch of constraints on a problem, I can't necessarily satisfy them all, but I can at least satisfy as many of them as I can. So the pseudo inverse is just going to get me at the X that gets as close as possible to making this equation true, is what you should think of it as. And generally, the more rectangular this matrix is, the harder it's going to be to perfectly invert it. But the pseudo inverse will always give me the closest X that's possible to inverting the matrix. And it's optimal in the sense of if I were to take the difference between the left and right hand sides, take the sum of squares to compute a scalar loss, this would be the solution that minimizes that. Okay, so to get an idea of what that looks like sort of in code, here I'm just going to define some random 50 by 10 matrix. So that's going to be the left-hand side here. X is going to be my unknown. And then B, which is my target, is going to be a 50 by 1 vector. And so the X that I'm solving for needs to be a 10 by 1 vector. And I want to find the 10 by 1 vector that, when operated on by A, will get me as close as possible to B. That's all I'm trying to do. Okay, so to do that, I'm just going to do the Moore-Penrose inverse. So I'm going to define this operation that just takes the SVD. I define the inverse as the matrix that takes the singular values. So this is this weird non-square diagonal matrix, and it's just going to flip every non-zero element over. So all those diagonal elements that were non-zero because of the spectral theorem, it's just going to take one over them just like we normally do. But the trick is that this is not a square matrix. So it's a little bit different than a normal inverse. Then I'm just going to quite literally take this definition here and write it in code form, and that's going to return this A plus matrix, the Moore-Penrose pseudo-inverse. Okay, so SVDs are pretty fast to compute. They're going to use the power method, which you use in your homework, to do it really quickly. And so this is going to give me the effective inverse of A applied to B. Okay, so I claim that if I messed something up. There we go. Okay, so I claim that if A at X equals B, that this should give me the solution for X that minimizes the difference between A at X minus B. Okay. So here I'm going to plot what I wanted, and then I'm going to plot what my pseudo inverse times my original matrix gate, or what the solution found by my pseudo inverse times X or times A gave me. And you can see it's not quite right? So if this was a straight line, that would mean that I got this perfectly right. But you can see there's a little bit of scatter. And that's coming from the fact that I had 50 equations, but only 10 variables I was solving for. And so it wasn't actually possible to satisfy every one of those constraints. So in other words, the Moore-Penrose pseudo-inverse isn't able to exactly solve this problem. It's just able to get as close as possible, or at least these two things are linearly correlated with each other. And if I were to relax this down to the case where maybe this was 10, I believe this would get a lot more accurate because now it would be able to perfectly satisfy. Let's see if I did that code right or if I messed it up. No, okay. So again, if my matrix is no longer overdetermined, it's able to exactly get this right. So everything is one-to-one equivalent. But it's really when I'm adding constraints. So let's try doing like 12 or something. Let's do 15. You start to see it picks up on a little bit of scatter. So as I'm adding constraints I can't possibly satisfy, my Moore-Penrose pseudo-inverse performs worse and worse. But this is still the optimal solution to this problem in the sense of minimizing the least squared error between the matrix multiplication with your solution and the true solution. Okay, so that singular value decomposition is generally useful for just analyzing large matrices and getting a sense of what they do and what their principal directions are. But it's also useful because it gives you the exact definition of the matrix inverse when you have a non-invertible matrix. All right, thank you.